Now, in the last class we discussed the how to sort an element using biotonic merge technique on machine on 2-dimensional mesh connected. Here we have not yet done the discussion on that how to know whether it is in increasing order or in decreasing order. If you remember, otherwise we mentioned S is your stage, and depending upon the stage number, S is your stage number. Depending upon the stage number, you have to decide whether the data you want to arrange, whether it is in decreasing order. Agreed? Now, so for that we introduce the term sign, the index comma S, sign index comma S. If it is positive one, then increasing order. Negative one, it is decreasing order. Now, in order to compute whether it is, you have to arrange it in increasing or decreasing order. What you do, that sin I comma s into your RR minus RS. If you find this is less than 0, suppose sin is plus 1. I told you that rejected element will be in RR register and accepted element will be RS register. Sin is suppose plus 1, then RR should take larger element or not. Plus 1 means increasing order. Plus 1 means it is in increasing order. So, RR should contain the rejected element, and RS should contain the accepted element. Now, if you find RR is less than RS, then only you will get the negative value, because this is plus 1. And if you get the negative value, that means RR is less than RS, and that means RR is containing the accepted element and RS contains the rejected element. Yes or no? Yes? If it is yes, then just you interchange RS and RR. So, what you do after in your routine, wherever you are using the base routine, row merge, column merge, and so on, you check sign of IS star RR minus RS less than 0, then RR should be interchanged with RS. Suppose the sign is minus 1, that means it should be arranged in decreasing order, and so this is minus 1 and this is 3 minus 5, suppose RR is 3 and this. So, you got positive value. So, RR is the rejected element, is RR will be this one, because this is positive, right, this into this is positive. So, you are going to arrange them in decreasing order, So, 5 should be kept in your area and 3 should be sent back. Okay. So, if you find that this is less than this, then you interchange. Now, how to compute this one? That is the problem yet to be solved. So, this definition is sign of SI is shuffled row measure index, row measure index of processor PI. So, each processor, if you remember, shuffle row measure indexing scheme. So, in shuffle row measure indexing scheme, can you tell me where will be your P0? Tell me. P0 is here, P1, neighboring one, P2, P2 is here, P3 here, P4, P5, right. So, the SI is the index of the PI's shuffle index of PI. So, sign is +1 if SI by 2 to the power S is even, and -1 if SI by 2 to the power S is odd. Let us see how it works. Tell me 16 random number, tell first number, 8, then 10, 1, 5, 6, 11, 20, 23, 22, 3, but 7, 9, 12, 14, 15, 7. So, let us assume that these are the 16 numbers you have and they are arbitrarily distributed. So, S equals to, first is S equals to 1, K equals to 1 if you remember in that. So, in S equals to, let us do it here, S equals to 1, first you introduce 0 by 2 to the power 1, okay, which is 0. So, 0 I assume even number, 1 by 2 to the power 1 is also 0. So, assume that it is also 1 plus 1 plus 1. Now, 2 by 2 to the power 1 is 1, which is odd. So, minus 1, this is also minus 1. 4 by 2 to the power 1 is even. So, this is plus 1, this is plus 1, this is 5 by 2 to the power 1, 6 by 2 to the power 1, 7 by 2 to the power 1, 8 by 2 to the power 1, 9 by 2 to the power 1, right. So, at the S equals to 1 at the first stage you get this. Now, you do the, you will be doing the horizontal merge, K equals to 1, 2K, so it is 8, 17, 1, 7, 14, 6, 22, 11, 10, 15, 12, 20, 23, 3, 9, 5, right. So, next time you will be calling vertical merge 2, 2. Before that, you have to fix your S equals to 2, vertical merge 2, 2. Now, once S equals to 2, 2 to the power S, 2 to the power S is 4, right. So, 0 by 4 is plus 1, plus 1, plus 1, plus 1. Now, this is 4 by 4 is 1, 5 by 4, 6 by 4, 7 by 4, 8 by 4, 9 by 4, 10 by 4, 11 by 4, 12 by 4, 13 by 4, 14, 15. Actually, you had this data 8, 7, 1, 7, 14, 6, 22, 11, 20, 12, 15, 10, 23, 3, 9, 5. So, if you do the vertical merge on this, so you will be getting 6, 8, 14, 17, 22, 11, 7, 1, 3, 10, 15, 23, 20, 12, 9, 5. Now you are in S equals to 3 and horizontal merge 2, 4. Yes, right. So, 2, 4, S equals to 3, 2 to the power 3 is 8. So, up to processor index 7, it will be 0, this is 0, so it will be plus 1. So, this will be plus 1, plus 1, this is minus 1, minus 1. You observe that this is increasing order, this is decreasing order. So, you can do the bitonic merge, horizontal merge. So, you get 1, 6, 7, 8, 11, 14, 17, 22, 3, 10, 20, 23, 23, 20, 15, 12, 10, 9, 5, 3. Now, you have S equals to 4 and you will be doing vertical merge 2 comma 2. So, basically 2 to the power S is 16 and all the first 16 processor will have 0. So, it will be plus 1. Right. So, this is increasing order, this is decreasing order. So, you can use the vertical merge and you will be getting you remember, right, how to do that vertical merge. What is that vertical merge? Huh? First column merge and then row. So, column merge and row merge. So, you will be getting column merge first. Can you do it yourself? You can do it and you will be getting 1, 3, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 17, 20, 22, 23. So, this is all about sorting on mesh connected computers. Now, can you tell me another model where bitonic merge or bitonic sort can be implemented directly? Can you give me another model where bitonic merge or bitonic sort can be implemented very easily? Let us start one by one. What is the next model? Hypercube? Okay. Let us think. Hypercube is what? Tell me, what is Hypercube? Hypercube is if you have 2 to the power n processors this is your 2 to the power n processor, this contains 2 to the power n minus 1 processors, this contains 2 to the power n minus 1 processors and each processor is connected with exactly one processor of the other sub hypercube whose MSB is different. Okay. Now, if it is the case, if the processor index is say Pi, then can you tell me what is the processor index of this? P to the P 2n plus 1 plus I, right. If it is the Pi, then this index is this. Agreed? Yes, any ambiguity? Puja is no, 100%. So, if this is capital N, so this can be written as n plus I. Agreed? Now, suppose this is in increasing order, and this is in decreasing order. This is increasing order, this is decreasing order. There exists a connection between these two processors. I can get this data here, compare and send back the rejected one here. Yes, according to the bitonic sequence property. In that case, this will be a bitonic sequence, this will be another bitonic sequence. All these elements will be smaller than every element of this. Yes, if it is the case, now this I can think about right, and I can proceed further. So, in order to do that, what should be the time complexity for merging a bitonic sequence of size 2 to the power n on a hypercube of size 2 to the power n? Tell me, is it a difficult proposition? This is clear, right? Yes or no? This is a bitonic sequence of size 2 to the power n on a hypercube of size 2 to the power n. Pi is connected with Pi plus 2 to the power n minus 1. So, I can bring this data from here to here in one shot, send back the rejected element after comparison. All these elements will be smaller than this element, and this is a bitonic sequence, this is also another bitonic sequence. Agreed? Now, recursively you call this one, simultaneously you can call this one also to merge. Now, if it is the case, so can you tell me what is TR 2 to the power n, what is TC 2 to the power n, and TE 2 to the power n? You do not need any high, what is that, at this stage you do not need any vertical merge, horizontal merge, just you bring this back, right. Tell me what is T routing, how many routings you need? Data is initially RR registered 2 to the power n, are you sure? What is distance? Why? What distance means that where? Where distance? What is that? This is one distance, one hop only. Because every processor has login connections, and this is one of them. You do not have to traverse this like that. Maybe wavelength is little more compared to that sub hypercube of this. And we assume that this length, speed of light is so fast that increasing the wavelength will not be that much effect. Let us assume they are all constant. So, in that case, one connection, here initially RR, so this is to be moved to RS, you will be bringing it here, right, and then rejected element will be sending back, and then you will be putting it again RR register. This is the steps involved, right. So, every time you will be giving one comparison, and it is hubbing it. So, how many comparisons you will be giving? N. So, this is clear. What about this one? Routing, how many routings? So, it is 2n. And how many So, bitonic merge on hypercube can be done. Now, can I use this idea for sorting? You observe in the case of sorting, it is basically bottom up, and while at the ith bottom you will be using top down. That is the idea everywhere. So, in the case of sorting, here it is increasing order, and within that you are putting the bitonic merge, right. So, at the ith stage you will be doing the ith bitonic merge. So, there will be n by I such merging technique, such merging subsequence you will be doing, right. So, that is the idea. In the case of hypercube, you have 2 to the power n processors. Here also you have S1, S2, S3, S is your stage number. This will indicate whether you are increasing or you are doing it in increasing order or decreasing order, and this sign functions you will be obtaining based on whatever you have done. In the case of mesh connected, Si by 2 to the power s, you observe this, basically this is a, assume that this is hypercube of size 2, this is another hypercube of size 3, this is another hypercube of size 16, and so on, right. And initially you have 2 to the power n, initially you assume that there are 2 to the power n sub hypercubes, each of size 2 to the power n, right. At the sth stage, you assume that there are 2 to the power n minus s sub hypercubes, each of size 2 to the power s, and compute sign function for each sub hypercube. And observe each sub hypercube is a bitonic sequence perform S is equals to 1, 2, how many times? S is equals to 1, 2, 3. Right. So, in that case, time complexity to sort an element or sort 2 to the power n element. So, I discussed this is the time complexity for the merging. Now, what is the time complexity to sort 2 to the power n elements on hypercube of size 2 to the power n? Tell me, quick. How did you get answer? Just random order? Not end to end. This is stage S. So, summation over S is 1 to n. So, you get n into n plus 1 divided by 2, which is order n square. No, this is S. It's the step like S. S varies from 1 to n. So, if I take, so you will be writing summation over S is 1 to n and which is order n square. So, similarly 2S and all those things. So, hypercube machine is very powerful for n elements, right. It is a log square time complexity, log square n time complexity. So, it is a log n factor away from cost optimality, right, log n factor, because cost is order n log square n to sort n elements. And you know sequential algorithm, you know lower bound is order n log n. So, log n factor is away from the cost optimality. Now, tell me, if first thing is that here you observe that what we assume that every processor is having one element, that means the number of processor is not adaptive, it is fixed. Now, what happens if it is you want to make it adaptive? Suppose you have P processor and n element, how are you going to do it? And what will be the time complexity in that case? Now, any idea? If you have P processors, hypercube, P processors and n elements, P is equal to 2 to the power m, P is less than n, and that is true in maybe you can think that it is a large, much large, smaller than n. That may be in reality, that may be the case. So, can you help me in sorting problem? How are you going to do it? Tell me. Yes, that is straightforward. Divide n elements into P groups, each group contains P elements. Right? Maybe the last processor will keep little less. They are not sorted. Huh? What is that? Okay. So, next is each processor sort elements in each processor. So, assign one group to each process. Then you told that sort elements of each in each group by each processor, right? Then you have got that this is sorted, and so on. You remember that by doing this, you have already created a problem. You lost the, because if you remember that you have to arrange the data in such a way that it becomes a bitonic sequence, right? So, this is increasing order, this is also increasing order. Here no longer the two elements is a bisequence, here not two elements, you have the two sequence. You understood the two elements forms a bitonic sequence of size 2. That property is not there, right. So, at s equals to, let us assume that s equals to 0, you are looking for the 0th step. So, at s equals to 0, all even index group should be in decreasing order. Not only you are making the sort operations at s equals to 0th stage, that even index processor arrange the data in decreasing order, and odd index processor, if your processor is 1, otherwise 0 onwards, then even index is in decreasing order, increasing order, odd index increasing order. So that your subsequences also form a bitonic sequence. Agreed? So, here you have to put s equals to 0, and what it means you have to write it here. So, you got the two subsequences in such a way that this is a bitonic sequence, this is another bitonic sequence, and so on. Now, what is next? Next is that you have to merge these two sequences using two processors. Earlier case, you brought this one element, you brought it here, compare it, rejected element you send back. Agreed? Here two processors and you have 2n by p subsequence size, and you have to do the bitonic merge. Yes? If it is the case, what is the time you did? One way, what is the, how are you going to do it? Tell me, how are you going to do it? The problem is clear, right? This is a bitonic sequence of size n by p. This is increasing order, this is decreasing order. You have two processors. Right? This is two processors, agreed or not? Now I want to merge it. No, there are n by p registered. Not in one register. One register can take only one element. N by p register. Yes, yes. Maximum you can use pipeline, nothing more than that, right. So, what see what you have to do, this whole thing you have to bring up, and you have to bring this one here, you want to do, right. This is one way. Another way could be 50% you send here, 50% you bring it here. Then you are trying to make busy both the processors, but you may not achieve, it is not that easy. Which 50% are you going to, because if you bring 50%, then also later on you have to merge it. So there is no guarantee, so you have to send the middle element here, middle element to this place to use the binary search, find out the which part of this is smaller than that you send. That is very, very complex. You won't gain much with respect to time complexity. So what best way is that, simplest way is that you bring this up, you bring this element, send back the rejected element here, and then you get, this is a bitonic sequence, this is another bitonic sequence, and you can merge. Now you independently you can do this bitonic sequence, right? Yes or no? So what I am telling, that you bring these elements here, compare all the elements, send back the rejected elements here, right, and accepted elements are kept here. Each processor can be used to do the bitonic merge of n by p elements, right. So you get a sorted sequence. If it is the case, what is the time you need to merge these two sequences, each of size n by p, by two processors? First you tell about the exchange operations. How many exchange? This you will be bringing up and again 2n by p, right. Okay, rest I will discuss later on. And then number of comparisons, only could you get him? Enters for this part, two sequence, two processors. If it is a binary sequence, so again log factor will be coming, right? Some factor will be coming. What is that factor? N by p half plus s. Also it is also in the term of n by p. This is also will be coming in the factor of n by p. Then routing, to n by p, right. So after doing this, you get increasing order, you get decreasing order. Next time what? Again. So this time data movement time will be much more, 2n by p. Here the size is n by 2n by p. Now this data, this you can bring it here. This, in order to bring it here, you have to pay a huge amount of time. Earlier this is connected to this. See, this box, this is connected, this is connected, this is connected, this is connected in Hypercube. Agreed or not? So this contains a sorted sequence, this contains another sorted sequence in decreasing order. Now if you want to bring this one, this whole thing here in this size, this is not a small task. Next time, task is increasing. If you have the another big size here, and you want to bring it here. Yes or no? So, can you think about this problem, how to sort n elements using P process? Now, I am silent about the biotonic. I am not telling that biotonic, I am increasing the complexity like anything. Why I shall use them in increasing order, decreasing order? Because once I have to merge the two sequence and just I bring all these thing elements and merge it. Merge takes how much time? N by P plus N by P minus 1, M plus N minus 1. Simple merging. So, this is also N by P plus N by P. So, in what way I am gaining? So, just I bring these elements here and merge it, simple operation. So, it is becoming 2n by P minus 1, right. Now, the problem is that you have to this is increasing order, this is also increasing order. Now, you want to merge it. So, basically you have this sequence form an increasing order sequence, this forms another increasing order sequence, right. Next is how to merge these two. Any idea? This contains all accepted elements, this contains all rejected elements, accepted elements, rejected elements, but there is no guarantee that these accepted elements are smaller than this element, right. No idea. No, if no idea, let us stop it here. We will go to little simple problem, then we will come back again, right, because that is the way one should think to solve a problem. So, let us think about this, keep it in mind, this problem to be solved. How to solve, I also do not know, you also do not know, that is the scenario, right. Yes. So, you have n elements, P processors, hypercube machine. This is the things to given for one element P equals to n, problem is known, biotonic is very good, right. If this is more than the n is more than much more than P, then how to merge this thing, that is to be seen. And now, in order to do that, first let us think about that. Suppose I have a linear array. I will come back to this again. If that linear array can help me in solving this problem. And this is the problem with mesh connected also, because it is not that easy to handle the scenario. If I have n cross n mesh, n cross n elements and P cross P mesh, how to sort it is not that easy. But sorting to ho jayega, but not the efficient sorting, it will be thing. Now, if in case of linear array, Suppose I have this array and each of them containing one element, each of them contains one element. Now tell me, how can I sort it? Do you have any idea? Have you heard the term? Odd even transposition sort. You will tell no, sir. Huh? Yes or no? What is yes? Yes is no. We have discussed in our class odd even merge sort. That is odd index, even index thing. And this is another sorting technique which is known as odd even transposition sort. Forget about parallel machines, let us come back to the sequential machine. Now, if you have x1, x2, x3, x4, suppose these 4 elements are there. Now, one thing you remember that in order to place x1, indirectly or directly you have to compare with every other element, right? That is there. Otherwise, if you cannot tell you get a sorted sequence. So, that arrangement has to be done. One way is that x1 has to be given a chance to compare with every other element. So, in odd even transposition sort, first every odd is compared with next even element. So, you get here x1 dash, x2 dash, x3 dash, x4 dash. The rejected element is in this part. Next stage, every even is compared with its next odd. Right? Now you get x1 double prime, x2 double prime, x3 double prime, x4 double prime. Next stage, okay, and then next stage this. So that will give you that x1 will be compared with x4. Everybody gets an opportunity to compare with every other, and in that case you can observe that there exists an inherited parallelism, right. So this can be done simultaneously, this can be done simultaneously. Agreed? So in the case of linear array, because this is very suitable for linear array, because pi is connected with pi plus 1, right. So for I equals to 1 to n by 2, there are n by 2 iterations are required, n by 2. For each odd indexed processor, pi do in parallel pi gets data from pi plus 1, compares and sends the rejected one to pi plus 1. So, the time complexity for this one comparison only, order 1, this is also order 1. I am assuming that transfer takes also constant amount of time. So, this is order 1 time, right, constant time. So, you have total time complexity is order n, right. You have 8 elements, 4, 1, 3, 6, 5, 7, 1, 2, 8. Suppose these are the 8 elements I have. So, you get 2, 6, 4, 7, 3, 5, 1, 8. You get 2, 4, 6, 3, 7, 1, 5, 8. You get 2, 4, 3, 6, 1, 7, 5, 8. You get 2, 3, 4, 1, 6, 5, 7, 8. You get 2, 3, 1, 4, 5, 6, 7, 8. You get 2, 1, 3, 4, 5, 6, 7, 8. You get 1, 2, 3, 4, 5, 6, 7, 8. So, you observe that I intentionally put 1 this side, so that you traverse, he gets an opportunity to traverse from one corner to another corner. Similarly, that 6 also got a chance to traverse his own position, right. But it is not a cost optimal algorithm. In sequential also it does not give you the optimal algorithm or lower bound algorithm. In sequential also it is order n square algorithm. Here also it is order n square time or order n square cost. Now, if you have a P processors and n elements, initially n by 2 P elements to each processor. Each processor sort this is now the problem is that instead of 5, 6, 7, 8 such subsequences if P equals to 8, and these are sorted. So, you observe that problem has come to similar nature, agree or not. So, our target is to break this problem. If we can break this problem, then you can solve the other problem. So, in the case of odd even transposition sort, this you have to bring it here, rejected elements you will be sending back, right. Similarly, is the case this and then this, right. Yes, if it is the case, can you bring this data here? and merge it, send back the data here, right. Parallelly these groups I can do. So, you need to bring this data, you need n by p times, and then merge it takes again n by p times, because merging these two sequences order n by p, sending back also again n by p. So, it takes order n by p times. Yes or no? Bringing the data from here to here, you need n by p, merge it n by p, send back n by p. Now, this data contains n by p sorted, each of them. Second time, you will be doing this, which is taking again n by p. Yes. Third time, which takes again n by p. Right. So, what is the time you need? How many each time you need n by p? Why? I am not increasing any size. Why 2 n by p? Where you are getting 2 n by p? Okay, sure. Hmm? And you will be doing p is there, so p by 2 times for odd index, p by 2 times for even index. So, p times you have to do it, right. Each time you need n by p. So, order n time is sufficient to sort it using p process. So, total time is required, total cost is n into p. So, it is cost optimal if p is log n of the order log n. Agreed or not? So, you try, rest you think and try to get whether similar idea can be used for Hypercube or not. First, you think whether a similar idea can be done for mesh.